Eighth grade lesson 8.5 is solving special systems. This kind of goes back to the previous chapter and brings back something that we worked on earlier where we had one solution, no solution, infinite many solutions. So we're just going to tie two pieces of already known information together. So let's do a quick review and then I'll show you how this looks. This is going to be a pretty quick one, I think. Okay, so let's take a quick review back to those infinite solutions, no solutions, one solution. So when we solved something and we had one solution, we would get something like x equals 5 or x equals 12 or x equals 100. It equaled one specific number, and that showed that one solution is the answer. If we were to graph that, it would look like this. You'd have a line, and then you'd have a second line, and it would have a meeting point, which you now recognize as the solution to a system. You have two different equations. Where they meet is the solution. There's only one meeting point. That's how that looks if you were to graph the system of equations. For infinite solutions, that was the ones that came out x equals x. Whatever x is, it equals itself. So for example, 5 equals 5 or 0 equals 0. So if you go through your system of equations and you solve it, you'll end up with something like that. 5 equals 5, 0 equals 0, 10 equals 10. And the reason it ends up like that, if you were to graph it, is you're going to get a line. And if you graph one equation's line, and then you go to graph the other equation's line, it ends up right on top. They're the same line. So it's because they equal each other. They are the same equation, just written in a different way. So that's what you'll see. If you were to graph those two equations, you'll see one line right over the other. And that means that every point on their line is equal to one another. That's why it comes out that way. Okay? Finally, for no solutions, those are the ones where it came out false. Something like 5 equals 3, or 2 equals 10, or 100 equals 50. Something that you know that's not right. And the reason they end up that way, if you were to graph them, is that you have a line for one equation and a line for another equation that happens to be parallel. They will never have a meeting point, so they never have a solution that matches. So that's how they look in graph form. One solution, you will have an intersecting lines with your system of equations. That's the answer to that system. If there's infinite solutions, they share every single answer on the line. They end up being the same line. And if it is no solutions, you will see two parallel lines. They will never intersect, so no solution. All right, let's look at 3 examples of those. Okay, so we have this system of equations, and we're going to go ahead and solve that. Remember, you have several ways you can do it. You can graph it. You can do substitution method. You can do the elimination method. And in that elimination method, if you don't have perfect opposites, you can manipulate them with multiplication to do that. That's my favorite method, so that's probably what I'll show you here. I'll look at these. I can make this become a -4, which would be the opposite of this. If I multiply by 2, that's probably the easiest way. So that's what I'm going to choose to do. So I'm going to multiply this whole equation by 2. Let me rewrite the top one over to the side here. I didn't do anything to that. Now let me rewrite the bottom equation with my multiplication by 2 to every term here. So times 2 to -2x gives me -4x. Times 2 to positive 3y gives me positive 6y. And times 2 to the 4 gives me 8. Okay, now I will simply add those two equations together. 4x minus 4x is 0. That was the elimination I was going after. Negative 6y and positive 6y is also 0, happens to eliminate. And a 9 minus an 8 is 1. So this comes out as 0 equals 1. And so if you remember, when we have something that's false, that means that I have no solution. When it's false, there's no solution. Those will be parallel lines, is how that will work. Let's see another example. I'm looking at these two equations. That's my system of equations. I'm going to again use the elimination method. I'm looking at a 1x and a 2x. I can get 1x to become the opposite of 2x by multiplying by negative 2. This one is probably easier to go with this one, it looks like. So I'm going to multiply this whole equation by negative 2. This bottom equation, I'm just going to leave it the same. Just going to write it over here. Okay, and the top equation, I'm going to multiply each of the terms by negative 2, so I can manipulate the whole thing to work in my favor. So a negative 2 times x is negative 2x. Negative 2 times a positive 2y is a negative 4y. And a negative 2 times 6 is negative 12. Now I simply add those together. You'll see the elimination happens right here. I have a negative 2x, you add 2x to it, and it's gone. That's why I did that. I have a negative 4y plus a negative 3y. That's a negative 7y. I went more negative. And a negative 12 plus a positive 26. That's going to be a positive 14. So here I have my equation of negative 7y equals 14. Now it's just a one-step equation. Y is being multiplied by negative 7, so the inverse operation of that is to divide by negative 7 to both sides of the equation, and that gives me y equals negative 2. So if I get an answer that the variable equals one specific number, that is one solution. That is one intersecting point that those two lines will end up having. So graphed, and I don't know, I'm not graphing the lines. They won't look like the way you would look if you graphed them. I'm just giving an example. They will intersect with each other, and that's their meeting point. Y would equal negative 2. And once I have that, I could go ahead and now plug in. I would have to go that step further, plug in y like we did before into either equation to solve what x is, because there is one meeting point. It is an x, y coordinate, right? So from there, I would go in, plug it into, let's say we plug it into the top one, minus 4 times negative 2 equals negative 12. This is positive 8 now. Let me just bring these down. And then subtract 8 from both sides. That's going to be negative 2x equals negative 20. Divide by negative 2, divide by negative 2, x equals positive 10. So you would have 10, negative 2. So if you get down to the point where you have one solution, pop it back into one of the equations so you can find the x or the other coordinate, the other point. So that's my solution. That's the one solution, and that's the one point that they meet at. Okay, and finally we have another. This is our last one we'll do, just so you can see. This is a system of equations, two equations here. I'm going to use the elimination method again. My x's, I have 12x and a negative 3x. If I multiplied this by 4, it would be negative 12x, so that would be good. I'm just going to go ahead and do that. It's the first thing I notice. So multiply that times I'm sorry, not negative 4. We want to do positive 4 because it's already negative. We want to leave it that way. So just times 4. So I will rewrite this top one just as it is. I'm not changing that one at all. I'm going to rewrite this bottom one with each term multiplied by 4. Negative 3 times 4 is negative 12x. 4 times positive 2y is going to be positive 8y. 4 times 1 is 4. That's a positive. Then I add those together. 12x minus 12x is 0. Negative 8y plus 8y is 0. Negative 4 plus 4 is 0. So I end up with 0 equals 0, which is true. This means I have infinite solutions. If I were to graph this on a graph, I would have a line for this one, And then if I graphed this one, it would happen to turn out being a line right on top of it because they share every single point, every single solution. So that's what happens with those. That's what this lesson is about. So it's no new calculating. It's the calculating that you already know. It's just recognizing those strange situations that may happen and how that looks graphed. Hopefully that clarifies all of that. Good luck with it.